Hi everyone, welcome back to another video lecture from Kim. Today we're going to be talking about what the pH and the pOH is, how to calculate those, and also we'll talk about the concentration of hydrogen ions and hydroxide ions, and also how to calculate those. So to start off with, the term pH, it actually came from the French, and in translation it means the power of hydrogen, and that's because we're going to see that we're going to be using this log scale, and so small differences can mean big changes. And specifically, pH is a measure of the concentration of hydrogen ions. And so we'll write it in these brackets, and that means concentration. And then, of course, like the H plus is your hydrogen ion in there. And one of the relationships you definitely need to know is that the lower the pH, the more acidic the solution is. So hopefully you're remembering that the pH of acids is less than 7. And again, we have a negative here in our equation, so we're going to see an inverse relationship between the pH and the number of hydrogen ions. And then another thing to think about when we talk about log scales, even though we might just have a difference between 3 and 4 and 3 and 5, a difference of 3 to 4 means that it's 10 times more acidic than a pH of 4. And a pH of 3 would then be 100 times more acidic than a pH of 5. So again, small numbers, just a change of 1, to us we think it's not really substantial, but when we're measuring the concentration of these hydrogen ions, it really does affect the overall concentration. So on the last slide, we saw the formula that we're going to be using for pH. And again, that formula is pH is equal to the negative log of the hydrogen ion concentration. So when we go ahead and we look at these examples, it's asking for the pH. Okay, cool, that's right there. And it gives us our hydrogen ion concentration. Okay, also super cool. So we're just going to need to go ahead and plug these values in. Now, after you plug that into your calculator, I'm hoping you're coming up with a pH of 4. But if you didn't, let me give you a few hints here. Remember, when you are using your calculator, you want to be using the button that probably looks like this, not the subtraction key, but the actual negative key there. And then when you're entering your value here, you would go, of course, your parentheses, but 1 second EE, and then you want to go ahead and use that little negative sign again, and then you're going to go to the 4th. So try it again and just make sure that you're ending up with the correct answer. Now let's do the same thing with number 2. This time you go ahead and plug it in. Pause the video and double check your work and answer with me. So hopefully your work looked like this. You did your negative log, and then you did your 3.25 times 10 to the negative 4th. And remember, for this one again, you would have gone 3.25, hit that second key, hit that EE key, and then done the negative 4 again. And then your answer for this one is not going to be exactly 4, notice that, but it's going to be 3.488. And one of the things that you're going to see, which I'm not testing in honors chemistry, but they do test, sorry about the bell, they do test in AP, is one of the things that you'll notice is whatever your concentration is, you want to see how there's 3 significant figures here. You have to have 3 decimal places when you do your pH. It's like one of those weird laws for logs for sig figs. But as long as you're in this ballpark, you're going to be doing good. Now, something that I do want you guys to notice is if we were to compare these numbers of 1 times 10 to the negative 4th and 3.25 times 10 to the negative 4th, yeah, they're both still not small numbers, but notice how this number is bigger. So this one has more hydrogen ions. And what did we talk about on the last slide? That there's an inverse relationship. So the more hydrogen ions you have, the lower your pH is. So you can see we have more hydrogen ions, we have a lower pH. Now go ahead, pause the video, solve number 3 and 4 on your own, and then go ahead and hit play, and let's make sure that we're ending up with the correct answers. Okay, so one thing I did just kind of fix from up above. A second ago I told you depending how many significant figures are in the concentration, that's how many decimal places you need to have. So up here, do notice how like there's 3 significant figures here. So my final answer over here for my pH should also have 3 significant figures. Then if then when we get down here, notice that my concentration only has 2 sig figs, so I'm only going to have 2 decimal places. Again, not the most important thing ever, but for AP, you'll see us talk about that. So when we go ahead for this one, we did the negative log of that concentration, and it ended up to be a pH of 11. And then notice this one had like a little bit more hydrogen ions. It had like a greater hydrogen ion concentration. So again, it's going to have a lower pH because the more hydrogen ions, the lower the pH. Again, that inverse relationship. Okay, well, if we can calculate pH, we can calculate the hydrogen ion concentration. And I'm going to use this term, and I feel like it's an old lady term, but y'all know that I'm an old lady. We're going to call this the anti-log. I asked our math teachers, they don't really have a good term for this. The old guys agreed with me to call this the anti-log. So before, a second ago, we were looking at our equation, pH is equal to the negative log of the hydrogen ion concentration. So we were able to solve for this. But what if we wanted to solve for this guy over here? Well, now we're going to use this equation. So really simple. We're just going to go 10, and whatever your pH value is, we're going to take the negative of it and plug it in. So let's go ahead and see a few example problems. And again, that equation that we're going to be using is our hydrogen ion concentration is equal to 10 to the negative pH value. So here, I'm just going to simply, okay, so let me slow down here. So we're looking for hydrogen ion concentration. So we're going to use this equation, obviously. So what I'm going to do is I'm going to write my hydrogen ions, and remember the brackets mean concentration. I'm going to go 10 to the negative 2.3. Let me plug this into my calculator. So hopefully when you plug that into your calculator, you came up with a value of 0.00501. Again, if we use those same log rules, it's just going to be 0.005 for the concentration of those hydroxide ions, or you could go ahead and write it in scientific notation. And so we would write it as 5 times 10 to the negative third molarity. That's what the big M stands for, okay? The concentration, again, that's the molarity is the concentration unit for concentration, and then HCl. Okay, so now go ahead, let's try number 6 and 7 on your own. Pause the video and come back and double check. So for problem number 6, I'm hoping you're coming up with something like 7.9 times 10 to the negative 14th in your calculator. And again, if we were doing this using those crazy sig fig rules, it would just be 8 times 10 to the negative 14th, and then molarity, and then of our hydrogen ions. And number 3 would give you a hydrogen ion concentration of 3 times 10 to the negative 8th. Okay, now I know this isn't like one of the questions on here, but I always want you guys to understand like conceptually what's going on here. So a second ago, I told you guys the larger your hydrogen ion concentration, the lower the pH would be. So hopefully you're seeing that relationship. So in this case, this has the most hydrogen ions, so it's going to have the smallest pH. If we look over here, this has the fewest number of hydrogen ions, and so notice it has the highest pH, so less and then higher pH. So now here are some questions that you probably should know, so please try these on your own and then I'll go ahead and go over them. Okay, so just to review, the pH scale generally goes from 1 to 14. Notice I put an asterisk there because when you get to AP Chemistry, this is a bit of a lie. You're going to see that some pHs are higher than 14, some pHs are actually in the negative range, okay? But for our purposes, we're going to say 1 to 14. What is the pH range of an acidic solution or of an acid? It's going to be anywhere from 1 to less than 7. Next one, what's the pH of an alkaline solution? You might also call this a basic solution. Well, it's going to be greater than 7 and go all the way up to 14. And then the pH of a neutral solution, as you've probably guessed so far, is 7. Okay, remember that's the pH of water. And then this next one, it's going to seem random, but it's going to make more sense on the next slide. What is the hydrogen ion concentration of a neutral solution? Okay, and it's actually going to be this value here. And remember, we could have calculated that by taking our 10 to the negative pH, or in this case -7, and we would have seen that we come out with 1 times 10 to the -7th. Okay, so the thing I'm hoping that you're noticing is that in this case, this like -7, the pH, and the exponent on the hydrogen ion concentration are going to be related. Okay, so we learned how to calculate the pH. So now we got to learn how to calculate the pOH. And so in this case, this is just the opposite. Remember, OH, or hydroxide ions, are referring to bases. So hopefully you've been taught, and remember, there are 2 earlier definitions of bases. So here's the Arrhenius definition. I may have misspelled that. I totally realize that. But what it says is that a substance that releases a hydroxide ion is going to be considered a base. And then Bronsted-Lowry, this is like the more modern one, not quite the most modern one, that's Lewis. But the idea here is we have ammonia, which is a weak base, reacting with, oh my gosh, I'm glad I just caught that. This should be water. Okay, reacting with water is going to create an ammonium ion and hydroxide. So notice in both of these cases, we're giving off hydroxide ions as a final product. So that's why we're using it here. So pH is measuring the concentration of hydrogen ions. pOH is measuring the concentration of hydroxide ions. And so I know you're going to be shocked, but we're going to calculate it the same way. So let's go ahead and look at this one. So to calculate the pOH, just like it says, we're going to go negative log, and this time they gave us the hydrogen ion concentration, so that's good. So 1.0 times 10 to the -3rd. Go ahead and plug this into your calculator, and you should be coming up with a value of 3. Make sure you're plugging it in. Now go ahead and try to solve this next one. So we're going to go ahead, do negative log, put in that concentration of the hydroxide ions, and we are coming up with a pOH value of 2.1. Now, if we were really following those rules a second ago that we were talking about for sig figs, this would be 3.00, and this would be 2.10. Now again, we might want to calculate just that concentration of hydroxide ions, and we can do that again if we know what that pOH is. And so again, we're going to use that anti-log here. So same thing, we're going to go ahead to find the hydroxide ion concentrations, add the negative pOH that we calculated. So go ahead, knock out 15 and 16, and after you plug these both in, hopefully you're coming up with our like 3.16 in that ballpark times 10 to the -5th, and like a 1.3 again in that ballpark to the -12th. Okay, so here is something that is super, super cool, and I love this. So there's a couple of things that you are going to see and be able to use to solve problems. Okay, so if we take our pH value plus our pOH, we're going to find that this always equals 14. Even a second ago, I know I lied to you, and I said, hey, AP chemistry, it's going to be negatives and it's going to be bigger than 14s. Even in that case, they're always going to equal 14. Something else that's really a cool relationship is anytime you take your hydrogen ion concentration, multiply it by your hydroxide ion concentration, it's going to come out with a constant value, remember constants stay the same, of 1.0 times 10 to the -14th. So what do these do? What do these help you with? Well, if you know the pOH and you need to find the pH, you just have to do some subtraction. And then the same thing, if you know the hydroxide, but you need to find the hydrogen ion concentration, you can just go ahead and divide 1.0 times 10 to the -14th by that hydroxide ion concentration to find the hydrogen ion concentration. So these are going to be super groovy and super helpful. So dun, da, da, let's use these cool relationships now. Okay, so in this first case, we're going to calculate the pH of a solution with a pOH of 9. And then we're also going to need to say if it's acidic or alkaline. Remember, that means it's basic. So in order to figure out this one, I just want to like remind us, we actually need to look at the pH for these. The pOH is not helpful, right? Because that's not how we describe something being acidic or basic. It's with the use of the pH. So again, we have our handy dandy formula. pH plus pOH is equal to 14. So what I can do to find the pH is I can take 14 minus the pOH, okay, to find our pH. And then I can go ahead, substitute those values in. So I'm going to go 14 minus 9, and I'm going to see that I have a value of 5, and this is our pH. So if we look at a value of 5 on the scale, we're going to see that it's in the acid range, right? Because remember, anything under 7 is going to be considered acidic. Now you go ahead, pause the video, and knock out number 18 here. So hopefully what you did here is you just took your 14, you minus your pH, and you were able to figure out that you have a pOH of 3. Now again, it's asking if it's acidic or basic. So again, remember we actually need to look at the pH. So we're not looking at this value, we're going to come back and use this value. So a pH of 11 would be, you guessed it, a basic or an alkaline solution. Now let's go ahead and look at this next one. So it's asking us to calculate the hydrogen ion concentration if we know the hydroxide ion concentration. So now we're going to use that other equation that we saw on the last slide. So we're going to take our hydrogen ion concentration times our hydroxide ion concentration, and it's going to be equal to 1.0 times 10 to the negative 14th here. And so in order to get, what are we trying to solve for here? We are trying to solve for our hydrogen ion concentration. Well, what we can do is we can divide both sides by our hydroxide ion concentration. Remember, I like to rearrange my equations first before I plug in numbers. It always seems to make more sense. So in this case, we're going to go 1.0 times 10 to the negative 14th, and I'm going to divide it by the concentration they gave us of 2.55 times 10 to the negative 4th. And when I do that and plug this into my calculator, and remember, it's going to be best if you are putting these parentheses around here to get that right answer. So go ahead, put it in your calculator, and let's see what you get. And I'm hoping you're coming out with a hydrogen ion concentration of 3.92 times 10 to the negative 11th. I know it's a little hard to see here, but negative 11th. So now, same thing, you go ahead, calculate number 20. And hopefully for number 20, you're coming out with a hydroxide ion concentration of 1.23 times 10 to the negative 11th. Okay, so one thing I would just want to show you real quick, kind of like another thing I want you to, notice that when we take these values, we have -4 and we have -11. And I know you're like, right now, Miss Semino, that adds up to 15. But is it pretty darn close to 14? It is. So if you know one of your concentrations, you should be able to make a good guess. Or like I always joke, my 4th grade math teacher said, check your work, see if that answer even makes sense. And so hopefully you'll see that those values are adding up to about 14. Okay, and so finally we've got some difficult problems. So we're going to need to be using those relationships between pH and pOH, as well as when we can multiply the hydrogen ion concentration and the hydroxide ion concentration to get that 1 times 10 to the negative 14th value. Okay, so let's go ahead, let's look at this one. Let's see what it's asking. So we're asking for the pH, but they're giving us the hydroxide ion concentration. So take a second and think about how you could solve this. Pause the video if you need to. Okay, while I think that there are different ways that you can solve it, I think what I'm going to do is I'm going to go from my hydroxide ion concentration, and I'm going to figure out what the pOH is. Okay, and then I'm going to be able to do that because I can take my equation of pOH is equal to the negative log of the hydroxide ion concentration. And then once I know what my pOH is, then I can figure out what my pH will be, and that will be, because I will go 14 minus pOH, and then I'll get my pH. So let's go ahead and run through that. So after I went ahead and plugged this hydroxide ion concentration in, I came out with a, oops, you guys do see my mistake here. This should be POH, right? POH. So this was equal to my POH. And now that I have the POH, I'm going to simply go 14 minus 9.26, and I'm going to come up with a value of, you guys can probably hear my calculator, I forgot to calculate this, and I'm going to say 4.74, and this, like I said, is going to be the pH. Go ahead, let's look at the next problem here. So it's going to ask, what is the hydrogen ion concentration of a solution with a pOH of 6.8? Go ahead, pause the video, come up with a plan to solve this problem. So for this one, I think the way that I'm going to solve it is I am going to go ahead, I know the pOH, so I'm going to find that the pH. So I'm going to go 14 minus my pOH, and so this will be 14 minus 6.8, and then this will give me 6.8. This will give me 7.2, so this is my pH. And then remember, if we use that anti-log, we can find the hydrogen ion concentration by going 10 to the negative pH. So in this case, it'll be 10 to the negative 7.2, and that is going to equal, I am coming up with 6.31 times 10 to the negative 8th, and again, that's going to be equal to our hydrogen ion concentration. So hopefully you're able to see how we're able to use both equations together to solve these problems. As always, please make sure you guys are writing down any questions you have and ask me in class. See you later.